Welcome to the first class of this course. My name is Filippo Morabito and I am your instructor. This course is intended to be an introduction to the differential geometry of curves and surfaces. This branch of mathematics consists of two parts. One focuses on the study of local properties of curves and surfaces. By local properties, we mean those properties which depend only on the behavior of the curve or the surface in the neighborhood of a point. The techniques that we will use in the study of these properties are those of calculus. The other part studies the influence of the local properties on the behavior of the entire curve or surface. In this course, we will focus our attention mainly on the local properties of curves and surfaces. In fact, only a small amount of time will be dedicated to the presentation of some global properties of curves and surfaces. The first part of this course deals with the curves. In the beginning of this lecture, I will introduce the definition of curve, and later on I will introduce the machinery needed for the study of curves. In the sequel, it will be very useful to see curves as mathematical tools for modeling the motion of an object. The first definition I will provide is the definition of parametrized curves. So let I containing R denote an interval that is a non-empty connected subset of R. It is possible to show that an interval can have only one of the following forms. So we have a finite length open set, a finite length closed set. Then we can have also sets which are nor closed nor open, of finite length. Of course, we can also have infinite length open set like this one. And sets which are of infinite length and which are nor closed nor open, like minus infinity b, a plus infinity, and the last one is of infinite length and open. Now suppose that the functions x of t, y of t, z of t are the coordinates at time t in I is our interval, of an object moving in R3. Then what can we say about the position of this point? We can say that the position vector of the object at the time t in I is gamma t, whose components are x of t, y of t, z of t. We will make also the following assumption. Gamma is a smooth function that is each of the three component functions x of t, y of t, z of t is smooth. That is, it is differentiable an arbitrary number of times. I would like to spend a few words about the definition of smoothness at a boundary point. I would like to point out the fact that the interval I we are considering can have boundary points. So what does it mean for a function to be smooth at a boundary point? So let's write remark, definition of smoothness at a boundary point. So if I is an interval containing boundary points, then a function f defined on I with values in R is said to be smooth if it extends to a smooth function defined on an open set, on an open interval which contains I. So in this case, what is the derivative of f? So in this case, the kth order derivative of fk defined on I with values in R is the restriction of the kth order derivative of the extension to the interval I. Let's see a simple example of this. So suppose we have a function f defined on the closed interval AB with values in R. What does it mean for f to be smooth? The function f is smooth if there exists a smooth function f hat defined on J with values in R, where J is an open set containing containing the closed interval AB. So for example, you can take J equal to A minus epsilon B plus epsilon with epsilon positive, and such that f hat of t is equal to f of t for all t in AB. In this case, the kth order derivative of f defined on the closed interval AB with values in R is defined as the restriction of f hat k, that is the kth order derivative of f hat, to the closed interval AB. Some of you would ask me the following question: does this characterization of smoothness depend on the extension we choose? The answer is no. So, final remark, it is possible to show that this characterization of smoothness does not depend on the chosen extension So, in other words, if you want to prove that a function f defined on a set which is not open is smooth, it's enough to find one extension of this function which is smooth on an open set containing the original one. If you want to know more about this statement, please see exercise 1.2, page 6 of the textbook. Now we are ready to present the definition of parameterized curve. Let's start by a simple observation. The function which models the motion of a point in R3 is gamma defined on I with values in R3. So we need a function with values in R3 with gamma smooth, of course, with gamma smooth. Of course, we can generalize this and we can work in a space of dimension n. So we can give this definition. A parametrized curve in Rn is a smooth function gamma defined on I with values in Rn, where I containing in R is an interval. Let's see a few examples of parametrized curves. First example is example of the unit circle. So the function gamma t equal to cosinus of t sinus of t with t varying in minus infinity plus infinity is a parametrized curve. In R2, we call it a plane curve. So we say it is a plane curve that describes the motion of an object traveling counterclockwise around the unit circle. Why this is true? Let's make a picture. So for any value of t, gamma of t is a vector having its tail at origin and its tip on the unit circle. If t increases, then how this vector changes? Very simple. It rotates this way. It rotates counterclockwise. So this is why this curve describes the motion of a point of an object traveling counterclockwise around a unit circle. The second example is one of the helix. So the function gamma t equal to cosinus of t sinus of t t with t once again in minus infinity plus infinity is a parametrized curve this time in R3. So we say that it is a space curve for this reason. And this curve describes the motion of an object traveling along a helix. So what is a helix? It's a subset over 3 whose projection onto the xy plane is a unit circle. Why this is true? Very simple. If we project a point of R3 having these coordinates on the xy plane, then this means that we have to drop the third coordinate. What we get? We get cosinus of t sinus of t, and if t increases varies from minus infinity to plus infinity, we've seen before that we have a curve describing the motion of an object traveling around the unit circle. While the z coordinate increases linearly with time. So let's make a picture. this is what you get. Third example. The third example is the example of graphs. So if I is an interval, and f defined on I with values in R is a smooth function, then gamma t equal t f of t is a parameterized curve which describes or models the motion of an object along the graph of the function f. So example, consider f of t equal to t squared. This means that gamma of t is equal to t squared and we can assume that t varies in minus infinity plus infinity. This is a plane curve which models the motion of an object along the graph of the function which associate to t squared. That is the parabola of equation y equal x squared. How can you find the equation? Very easy. You look at the component functions of gamma. This is x of t and this is y of t. What is the relation between y and x? Very easy. Y of t is equal to x of t squared. Example number 4. Straight line. The plane curve gamma t equal a plus ct b plus dt with t in minus infinity plus infinity and cd different from 0, 0 describes the motion of an object along a straight line why this is true? First of all, we write gamma of t in another way. We write gamma of t as AB plus t times CD. So this means that for any value of t, this vector is the sum of a constant vector plus a vector whose length varies linearly with t. So let's try to make a picture. Suppose that this is the vector AB and this is a vector CD. So if t is 0, gamma of 0 is just A of AB. So this means that the position vector gamma 0 coincides with the yellow vector AB. What happens if, for example, we take t equal 1? We have that gamma 1 is AB plus CD, and using the parallelogram rule for the sum of vectors, you get that gamma 1 is this vector here. You can continue. What happens if t is 2? You get the gamma of 2 equal AB plus 2 times CD. So this means we have to consider the sum of AB with a vector having the same direction as CD but the double length, which means this vector here. And this time the vector gamma of 2 is the sum of the yellow vector AB and this new red vector. So you get that gamma of 2 is this vector here. And of course you can continue. If we take t equal 3, then gamma of 3 will be equal to AB plus 3 times CD, and in the end you will get a straight line if you let t vary in minus infinity plus infinity. The next topic I will present today is the derivative of a curve, and I will also talk about its geometric interpretation. So, derivative of a curve and its geometric interpretation. So, definition 1.6. So, if gamma from I with values in Rn is of course a parametrized curve, with components, with component functions, x1 of t, x2 of t, xn of t, then its derivative is the parametrized curve defined by gamma prime of t equal x1 prime of t, x2 prime of t, xn prime of t. Of course, you can also define higher order derivatives, and what is their definition is perfectly similar to this one. So I will write just that higher order derivatives are defined in a similar way. So this definition says two things. The first one is that the derivative of a curve is a curve, and the component functions of the derivative of a curve are the derivatives of the component function of the original curve. In order to present the geometric interpretation of derivative of a curve, I will give you an equivalent definition which is contained in this proposition. the derivative of a parameterized curve gamma defined on I with values in Rn at time t is equal to gamma prime of t equal limit as h tends to 0 of gamma t plus h minus gamma t over h if t is an interior point and it is equal to gamma prime of t equal limit as h tends to 0 plus gamma t plus h minus gamma t or h or gamma prime of t equal limit h tends to 0 minus of gamma t plus h minus gamma t over h if t is a boundary point. So for example, let's consider the case where I is a B closed on the left but open on the right. Then in this case, if you want to compute gamma prime of t for t in AB can be computed using this formula. Instead, if you want to compute gamma prime at A is a boundary point, so you have to use one of these two formulas. Which one? The first one, because the function gamma is defined on this set here, and t can take values larger or equal to a, so you have to choose h to be positive, and while considering this limit, h must tend to 0 from the right side. So gamma prime A is a limit as h tends to 0 plus gamma A plus h minus gamma A divided by h. Now let's give the geometric interpretation of the derivative of a curve. And let's make a picture. So we consider the simple example of a plane curve. For example, this one. And let's suppose that the position vector at time t is this one. And the position vector at time t plus h is this one. Then how the vector gamma t plus h minus gamma t looks like if we draw its tail at the tip of gamma t? Very easy, the answer is this. This is a vector gamma t plus h minus gamma t. So what happens if we divide gamma t plus h minus gamma t over h as suggested by this formula? We get two things. One, the length of the vector star, where star is this vector here, approximates the speed of the object This is clear from your course of physics. And we have also a second property, its direction, the direction of the vector star is approximately the direction of motion for h small. So what happens if h tends to 0? Let's make another picture. This is the same curve as before. If h becomes tends to 0, then according to the definition of derivative I gave, we get that this vector tends to gamma prime of t, and if we draw this vector such that its tail coincides with the tip of gamma t, we get this vector here. This vector has two properties. Can you guess what are these two properties? One, gamma prime t is tangent to the trajectory of the object, and two, the length of gamma prime of t is the speed of the object. We call this vector velocity vector for these reasons. Okay, the last definitions of today are those of speed and arc length. Speed and arc length. So, definition 1.8, the speed at time t in I of a parameterized curve gamma defined on I with values in Rn is the length of the vector gamma prime of t. Clearly, this definition is justified by the discussion we made before. What about the arc length? The arc length between times t1 and t2 is defined to be the integral from t1 to t2 of the length of gamma prime t dt. Now I will introduce a special class of curves known as regular curves. These curves have the property of having speed always non-zero. So let's write down the definition. So let gamma defined on I with values in Rn be as usual a parameterized curve gamma is said to be regular if the speed is always non-zero A special case of this is the following. It is said to be unit speed if the speed is always equal to 1. Before writing down the definition, I would like to say that we can also call these curves parameterized by arc length. If, as I told you before, gamma prime of t is a vector of length 1. Let's try to understand why we call these curves parameterized by arc length. So origin of the expression parameterized by arc length. Let's try to compute the arc length between times t1 equals 0 and t2 equal t for a unit speed curve. So this means that the gamma prime of t is a vector of length equal 1 for any t in I. So we get the integral from 0 to t of gamma prime tau d tau. Here I am obliged to use a different variable of integration because the upper bound of integration is t. And if you compute this simply, the integral is equal to t. So this means that the arc length between times 0 and t coincide with the value of the parameter t. So this explains why we use the expression that the curve is parameterized by arc length. And now I will provide you with some examples. So example of regular curve. So let's consider gamma t equal cosinus of t sinus of t. What is the length of gamma prime t? This is the length of the vector minus sinus of t cosinus of t and it is very easy to see that this is equal to 1. So this is not only a regular curve but also a unit speed curve. So it is a regular curve, but it is also a unit speed curve. And now I will finish the lecture by giving you an example of irregular curve. That is a curve which is not regular. Let's consider gamma t equal to t cubed t squared with t in minus infinity plus infinity. This is a plane curve which is not regular. Why? Why? Because the length of gamma prime t is the length of 3t squared 2t, and this is equal to the square root of 9t4 plus 4t squared, and this is 0 if t is 0. So let's observe the fact that the component functions of gamma are smooth functions they are x of t equal to t cubed, y of t equal to t squared, and they satisfy the equation y of t equal to x of t power 2 over 3. So this means that the curve describes the motion of an object moving along this trajectory. So this trajectory is a cusp. At the origin. This example here is interesting because the trajectory has a sharp point at the origin, even though the component functions are smooth. So this is a property that non-regular curves have. For today, that's all. Thank you for your attention.